Okay, now officially we start the meeting. Again, hello and thank you everyone. So a few notes before the presentation. The Shasta surface water groundwater model and model report posted on our webpage includes only base case scenario and unimpaired flow scenario. So we have only two scenarios with the results in the model report and the model results. Additional scenarios will be evaluated after verification of the model and confirmation that the model is sufficiently calibrated and robust to produce reliable results. So we are in the verification process of the model. So when we ensured about the calibration and robustness of the model, so we're going to go ahead and run other scenarios. So your comments represent an important step in the verification and improvement of the model. Just with the comment that we need your comments to be sent to us as a written comments. Today's meeting is about the questions and kind of having more information about the model with you. But if you have any comment regarding the model, please send it to us via email. After public comments are received and addressed, the model report will undergo a Cal EPA external peer review process. So if you would like to know more about the details of the Cal EPA peer review process, please go to this website and they have a very detailed information about how the external peer review process for the models is done. Well, this Shasta surface water groundwater model serves as the foundation for two additional watershed-wide tools for the Shasta watershed, a water temperature tool and a water allocation tool. These tools are under construction. So after making sure of the well calibration of the model, this hydrology model, we're going to go ahead and have the water temperature tool and water allocation tool finished and prepared for the Shasta River watershed. John, would you please go to the next slide? Okay. Just as a reminder, and you have already received it from the notice, but what we have posted on our webpage is, well, if you go to the Scott River, Shasta River webpage with the address that you see here, and if you go to the bottom of that page, you will see the long-term flow efforts. This is the section that we post all the news and all the updates regarding the waterborne long-term flow efforts in Scott and Shasta. If you go there, the final bullet says May 7, 2026, and that's the notice that you have already received. If you click on the keyword water model, you can go to the link to download the model. And I may recommend you to please do that before our next workshop. If you're willing to attend that workshop, please go ahead and download the model before attending the next week's workshop, which is all about the technical aspects of the model. In addition to that, if you go to that keyword model report, you will receive two documents. And I would like to, emphasize on that. There are two documents for your review and comment. One is the model report, and another one, which is actually a PDF model, is the Shasta River watershed schematic. That's a watershed-wide schematic that's been used for modeling, not just for this hydrology model, but it's going to be used in the water temperature tool as a reference for water temperature tool and the water allocation tool. So please go ahead, review that. And if you have any comment regarding the schematic as well as the model report, please let us know. So this was my very introductory slides to share with you. And now I may ask John to please go ahead and start the presentation on the hydrology model. John, please go ahead.
All right. Thank you, Shahab. Well, it's a pleasure to be able to share some of this work that we've been working on for a few years with you all. I'm joined by my team here. Vivek and I are going to co-present today's presentation. So just to give a brief overview, some of the objectives, drivers behind this effort. In 2014, the California Water Action Plan set forth these objectives of more reliable water supplies, restoration of important species and habitat, and also to create a resilient, sustainable, managed water resources system. So by taking those objectives in our modeling, our goal was to take the highest resolution information possible, combined with local information, to quantify existing conditions in the watershed, and then also to estimate unimpaired flows by essentially turning off anthropogenic components in the system. So all of this gives us objectively, the end goal is to have a system that we can use to then speak directly towards environmental flows and essentially be able to hone in on those key portions of the hydrograph that are important for the alternatives that we want to run. So just to step back, just to give a high level overview of our modeling philosophy. And at the beginning, the first effort in the beginning of this whole project was to get all the available information and see how and where there might be gaps and how and when we can use it in the process. That available information was used in conjunction with a segmentation process where we broke the watershed into catchments, hydrologic response units, each with properties that we'll go into a little bit more detail. We also derived forcing functions, boundary conditions that were used meteorology to characterize weather conditions throughout the watershed. So this configuration component, I would argue, is probably the most important part. And then as we went into the calibration process, the objective there was to adjust rates and constants to try to best estimate the physical processes and responses, confirm those responses against observed data at key locations. And then ultimately, at the end of this process, the modeling exercise itself, I would argue, is probably the value of this whole effort is it gives us a chance to see where we might have gaps in our understanding, where we can go and get better information and learn from our system and improve the system. And so a living model is one that is alive. It teaches us and allows us to continue to improve the system. So Shasta River watershed. Here we have some of these stats, which I think all of you attending this are interested in the watershed. You are probably well aware of some of the key features and characteristics of this watershed. 794 square miles. Klamath River is the main watershed that Shasta drains to. The geology is quite unique. When you look at this from aerial photographs, you see green and brown areas of the watershed. There is a lot of water movement, agricultural activities. It's a really important component of the economy there is the agriculture and so on. And so it's a really interesting watershed with lots of moving parts. So instead of just telling you about it, I'll just show you a few slides from our site visit. This was a watershed tour that we took in 2018, I believe, at the beginning of this. So here we are at the confluence of Parks Creek, upstream of the confluence of the Shasta River watershed. So you can see it's a really green and lush watershed. Streams, sort of almost alpine-like streams flowing down from the mountains there. And then here we have the confluence of Parks Creek and the Shasta River. This is the Big Springs complex. Had the opportunity to just stick my hand in there, and that water is quite cold, about 13, 14 degrees Celsius. So definitely an amazing thing to see. And then here's Little Springs. You know, as you're just walking these fields, there's water bubbling out from under the ground. It's an amazing thing to see. Here we see the Shasta River below the Big Springs complex. And then moving farther downstream near Montague, here's what the Shasta River looks like as we near the mouth of the watershed. So here we have had some diversions that have taken place, irrigation activity to support agriculture and the livelihoods there that have happened. And by the time you get to the very mouth of the watershed, it's a very different looking river system than what we saw at the beginning. And so you can imagine as a modeler coming into this watershed, it was quite interesting because in most cases, you generally have more water at the outlet of the watershed than at the headwaters. But this watershed provided us a really unique opportunity to characterize all the things that are happening in terms of the water movements and the impacts on environmental flows. So just to give you another schematic overview of the integrated modeling approach. As I mentioned, we begin with the weather data as the key driver for hydrology. The model is, we do some verification of that weather data to make sure that it's spatially and temporally representative of the climate conditions throughout the basin. You've got high elevation, low elevation areas, and quite a dynamic system in terms of weather variability. We also look at the response of the hydrology model against those forcing data. So we can see runoff, interflow, groundwater behavior. In portions of the watershed, the groundwater is a pretty important driver. And so this was part of the reason and the rationale for doing this coupled surface water groundwater model. And so here we have the opportunity to take the portion of the water that goes subsurface, and that becomes the boundary condition for the mod flow model. We'll give you a little bit more of that detail as we get into this presentation. And then the mod flow model predicts the groundwater returning back to the streams, seeping back to the streams. And so it is an interactive thing because it is also possible for water from the streams to enter the groundwater system. So really neat exercise, really neat opportunity for us to do this kind of a dynamic modeling system. And as you can see, all of these pieces kind of build upon each other. And so important in the whole process is making sure that at each of these different steps, you're informing the model with the best information possible. That's what's going to minimize the propagation of the error throughout your system. And so you'll see as we present some of the details why we spent so much time and effort on some of these intermediate components, because all of them are the building blocks for telling the ultimate story of the hydrology that's happening in the watershed. Land cover and land use. This is what represent the key building blocks of the model. We use hydrologic response units, which are combinations of land cover, land use, soil, slope, and geology. And so these different combinations are then used to characterize the way that a unit of land is going to respond to a meteorological forcing. Or in the case of an irrigated land, you might have meteorological data as well as imported water or diverted water that's irrigated to that same footprint. It's going to give a unique response. And in our modeling effort, our goal was to make sure that if we parameterize one of these unique hydrologic response units, it's the same parameterization regardless of where it is. The thing that's going to vary from place to place is the meteorological conditions and the irrigation. And so fundamentally, we want to stack the pieces together so that you're not overfitting the model to meet some objective at some point. We want to characterize the hydrologic principles based on the properties of land use, soil, slope, geology, and then let the meteorology kind of do the rest. Here's another view of things. We have information about where and when irrigation is happening and from what source irrigation water is derived, if it's taken from surface diversions or if it's from groundwater. Some of that texture is all baked into the model. When we move below the surface, we have geology attributes as well as hydrologic soil groups. And these soil groups, A soils, B, C, D, essentially think of them as well-draining, poor-draining soils. In the A category, we have better well-draining soils. The water tends to move subsurface. In the D areas, we tend to have water kind of standing on the surface a little bit longer, and you have the whole gradient of these responses in between. So these hydrologic response units, here is a summary table of just how the percent area is distributed by land use, soil, slope, and geology across the whole Shasta River watershed. So if you look at just total area, for example, it's about 36% of the area is classified as forest. Within that forest slice, for example, 46% of that area is A soils, And then from a slope point of view, about 57% of the forest area has slopes somewhere between 15 to 35%. The geology tends to be mostly cascade. That just gives you some feeling and some feel for the texture of the information used to characterize the unit responses. Now, these hydrologic response units get rolled up by subcatchment, so then we can route the surface components. Or in the case when we link to ModFlow, these HRUs can be rolled up by the ModFlow grids to figure out how much water moves vertically down from the surface into the groundwater realm. And so these are the basic building blocks of the model. Step two is to force the model using meteorological data. And we use a combination of PRISM and NLDAS. PRISM is a data source that provides at a 4 kilometer resolution a highly variable spatial time series of rainfall. Now, this rainfall, it's at a 4 kilometer resolution, so you're able to see even how it's averaged here in this picture, how that variability kind of plays out throughout the system. With the rainfall, we disaggregate it down to an hourly time step as to use to drive the LSPC model. Now that hourly time step is then essentially, the 4 kilometer monthly time series are disaggregated down to hourly at each of these locations. So when you smash these two together, we end up with 124 unique sets of meteorological forcing data that are used to drive the model across the watershed, which is pretty robust. It makes sure that, we're really characterizing what's going on. Now let's look at this a slightly different way. This is rainfall. And what you see in the bars are the average rainfall for all the different grids. And then on the brown line is the elevation of those grids, like the elevation of the centroid of those grids is plotted. So as you might expect, as you move to higher elevations, you tend to see generally a little bit more rainfall. It doesn't follow a straight one-to-one line because there are other factors going on. Factors such as hill slope aspect. So here's the same information plotted in a slightly different way. I have two x-axes on my lower plane. One is the median elevation, and then the other is the hill slope aspect. And if I was to take a transect across this plane and just look at all of the hill slope aspect variability along all the cells that have on average about 4,600 4,600 feet elevation, you can see that the east-facing grid cells tend to have more rainfall than the south-facing grid, south and west-facing grid cells. And those of you who are familiar with this watershed and just in general, even living in California, the weather gradients tend to move from the west, and then when they hit the mountains, a lot of water gets deposited. And so it makes sense that something like aspect would have an impact on the rainfall. But this is just to give you some texture and some feeling of the type of data that's used to drive the model. It inherently has some of this in here. And therein lies that key. If we're using the best information possible to drive the model, then it means that down the process, when we start calibrating, we're not going to have so much reliance on our own interpretations and button pushing and turning and tuning for calibration, because we have a lot of that variability is already baked into our forcing data. So it sets us up well so that there's less, burden for calibration to get the answer or the response that we need in the system. So it's an important component. Now, even within the calibration story, we start at the very top with snowfall calibration, because ultimately snowfall changes the timing of when that water is available in the system. Snowfall is essentially acting like a reservoir. So in certain places, you're going to have snow that's going to be stored for several months. And then when the spring snowmelt comes, that water gets released. Think of it like a reservoir. It gets released from that snowpack reservoir, and then it becomes available for hydrology. And so we wanted to also make sure that the model prediction of snow is spatially relevant and realistic based on what we can observe. So we had a few gauges throughout the watershed where we had some snowpack measurements that we could compare the modeled snowpack against. And there was one gauge at the Big Red Mountain, which was a snow telemetry gauge. It's 50 miles sort of northwest of Wairika. What's nice with that is it has snowpack on a daily basis for multiple years. And so going back to the first principles, if our model is based on the process and we can simulate and represent that snowpack at that level, and then transfer those parameters to a data set where we don't have daily resolution, we only have monthly. We can use that sort of like as a second validation of how things are going. That's kind of the line of thinking that we went about with this. I'll first show you some of the snowpack at some of these gauges within the watershed. So this shows the modeled response using the same snow parameters at two different locations, the Parks Creek snow telemetry location, and then on top of Mount Shasta. The first thing you see right away is one stack is much bigger than the other. And that is already sort of baked in because, of course, on top of Mount Shasta, there's a lot more precipitation that happens. It's a higher elevation, which means that it's going to tend to fall more as snowfall than near Parks Creek. These two locations are actually pretty close to each other, not too far away as the bird flies. But because of the elevation difference, we can see that it's quite a different story in terms of the available water that gets stored in the snowpack. So the modeled is the orange. The observed monthly dots there are the observed snowpack. I think they were measured like in April of of so the middle of the month for those months during the time when we have snowpack. And so here you see on the bottom is an annualized version where we take all the October 1st, all the October 2nd, 3rd, all the way for the whole year across all time, and then plot them against each other. So in both ways, we see the model is able to pick up temporal variability, and it's also able to pick up the spatial differences in the snowpack. Here's the other data, which this is outside the watershed, but using the same parameters, we looked at how the model performs at the Big Red Mountain snowtail gauge. And we were pretty encouraged to see that it did pretty well. You know, there's some years where it will overpredict and a few years where it might underpredict a little bit. But on average, this was capturing the tendencies and the relative magnitudes of available water in the snowpack was captured. And so that's good. If you're starting off with the model and that's way off, it's going to be a lot harder to get the model to predict stream flow, like at the mouth of Wairika, if some of these things aren't aligned first. So it's that sort of top-down, weight of evidence-based approach that we use to build the model. We did sort of late in the game get access to another data set, which is out of UCSB. They have a snow model that's at a 500 kilometer resolution. It is a model, but what was neat with it is it does show the spatial variability of snowpack in the Shasta. And you can see there's a big gap in the middle where the model domain doesn't actually cover because there isn't really a lot of snow activity or lingering snowpack in that portion of the watershed. It's really kind of concentrated in the mountains, sort of like bowl, the edges of the bowl, if you will, is where you're going to see the snowpack. And we looked at how our modeled responses track at each of, sort of sampled sort of the distribution of snowpack across that model domain and compared it with our model at those locations. And we saw it was a pretty tight agreement. So here are two of those points, A and B, shown here on the right graph of the UCSB model. And then what you're seeing in the left, the blue dots represent the UCSB modeled snowpack, and then the orange lines represent LSPC modeled snowpack. And so you see in general, there's a good agreement. Now, of course, the UCSB model, you can see every once in a while it kind of plateaus off. It is a model and it has its own sets of constraints. So there, in certain conditions, the model wasn't able to predict above a certain level. But LSPC was able to capture some of that. So again, it's one data source and one study compared against the other. But really, the point of the exercise is we want to look at everything that's available because all these different data sources are all important to telling the story and giving confidence that we actually have a system that is representative of reality. And so we looked at how all these available data and all these other studies looked simulated and estimated snowfall in the system. All right. So we talked about our segmentation, HRUs. We talked about our snowfall segmentation. Another key part of the picture here is the irrigation activity. And so we had information about the crop and irrigation source areas. And based on that information, we were able to kind of summarize how much water is available or the irrigation demand looks like from surface versus groundwater. The pumping volumes across the watershed, we summarized some of this came from David's Engineering, where they had done a pretty detailed study of irrigation demand across the watershed. Here we can see sort of like an average temporal distribution of source water, surface water versus groundwater sourced areas. And so what you're seeing here is that there's variability in the irrigation that's happening in the watershed. In our model, we try to find that centralized tendency and make sure that over time, what I'm showing here in this next graph, over time, the long-term cumulative volume of irrigation water matches what was deemed to be representative from the David's Engineering study. So year to year, you've got irrigation demand. You've got some wet years, some dry years, some overs, some unders. But in the long run, we wanted to make sure that our model, given the 12 monthly ET coefficients that we can tell the model to apply against the observed ET data, we wanted to make sure that that long-term trajectory was consistent with the David's Engineering study. And so that is how we sort of represented the irrigation activity. There's a little bit more to that, which we'll get into a little bit later. But let's talk now about this process of linking the surface water to the groundwater model. So LSPC and ModFlow. LSPC is the loading simulation program in C++. And ModFlow, as you know, is the groundwater model component. And one of these LSPC is the surface water component. It's a strong surface water model, but it has a very simplified representation of groundwater. And so the green box that you see here, the parameters that have sort of been canceled out, if we were running LSPC by itself, those are the knobs that we would have to turn to represent groundwater. And I talked about how each of those hydrologic response units are characterized. In LSPC, the HRUs are all next to each other. They don't talk to each other. There isn't that lateral movement like you have in ModFlow. And so what we did was we cut out that green box, and then everywhere where an HRU goes into the ground, we send that to a ModFlow grid. So that gives us the ability to then simulate the lateral movements of groundwater. If there's groundwater happening at different points in the system, we can remove water from the groundwater and then have a drawdown of the water table, which is going to affect how much of the seepage comes back to the stream from the ModFlow model. So here's that sort of feedback loop. GUI is this term that represents the input to ModFlow, and then AGWO represents the return out of ModFlow to the stream, or the movement from the stream back into ModFlow in the case of like a losing stream segment. All those things are possible in the system. And so this is how we ended up representing the linkage. So now let's just step back and talk about one other fine detail. After this, I'm going to hand it to Vivek to get into a little bit more detail of what's happening in ModFlow. But here we start in LSPC. We're in the surface water realm. LSPC gives us the ability to characterize diversions, irrigation, return flows. LSPC predicts surface runoff and interflow from the surface. It does predict the active groundwater outflow, but that's the part that we're cutting out and replacing with ModFlow. So when you intersect the subcatchments with a ModFlow grid, you are then able to resample the HRUs that were originally draining to the stream segments on the surface side. We can resample those by ModFlow grid to get unique GUI boundary conditions for each grid that are made up of the flavor of the HRUs that are existing within that grid. You'll see some of the views from the ModFlow results presented in the next couple of slides. ModFlow then is going to simulate the movement of water subsurface at a monthly time step, and then using the GUI that we provide from LSPC, as well as in certain cases, there's canal leakage, which becomes another sort of a GUI into the ModFlow system. ModFlow then predicts withdrawals or pumping from the groundwater, which causes the drawdowns and the movements of the water table. And then ultimately, the net outflow from ModFlow, the AGWO, we're calling it AGWO because that's the term that LSPC uses. That AGWO then cycles back to the stream. So when we get to the stream segment, the AGWO from ModFlow is compared against what AGWO LSPC was trying to predict, and we can calculate a delta. Now, this delta is then applied to the original LSPC model to come up with the same long-term average ModFlow net outflow, and it can be plus or minus from the stream. And we had to go through this iteratively a couple of times until we got a stable response. But that's how we ultimately invoke the coupled model. So at the end, we have SURO and IFWO from the surface water, and then we have a net AGWO in or out from the stream from ModFlow. And that's how the ModFlow linkage is achieved. Yes.
I'm sorry, John, that I interrupt you. Before you go ahead, since we got a question, would you please once again explain what an HRU is and how it's determined?
Awesome. Yes, an HRU is a hydrologic response unit, and it is a combination of land use, hydrologic soil group, slope, and geology. And so those four features, you can imagine if you intersect all those different possible combinations, you get quite a, hundreds of possible different combinations of hydrologic units per subcatchment. And that's the key building block that LSPC uses to simulate hydrology at the land level. The HRUs are then rolled up by subcatchment and routed to the stream. That's if you were running the surface water by itself. But since we're modeling with a coupled ModFlow model, the surface pieces go to the stream, but then we can also resample the HRUs by the ModFlow grids to get a unique representation of the vertical movement of water from the surface to the groundwater. And so that's where the HRU is resampled by ModFlow grid. That's where we get a unique GUI per ModFlow grid that's composed of the flavor of HRUs within each of that ModFlow grid. So HRU, think of it as just like the basic building block of the model. And then the subcatchments and the ModFlow grids are like cookie cutters that we can intersect the HRUs with to get a different combination of hydrologic responses to send either to the surface or to the groundwater. I hope I did that justice. Hope it's
Thank you,
clear.
John.
Okay.
Thanks, Sean. And yeah, Thanks, John. That was great explanation on how uh, essentially between LSPC and ModFlow, what the spatial upscaling is, and then also temporal upscaling from hourly to monthly, and how when information goes back from ModFlow to LSPC, how that is again downscaled to different space unit and time unit. So that was great introduction. Thanks, John. And I'll dive right into the subsurface. What you're seeing on your screen is the distribution of aquifer properties in the ModFlow model. Layer one is the shallowest, and then going through layers one, two, three, and four. There are four layers in the ModFlow model. Each one has a different distribution of aquifer materials in the subsurface. And as you can see in the legend, on the west, the purple color is representing Klamath Mountains. And on the east, a lot of it is mostly volcanics. And as you can imagine, with volcanics, it becomes really a challenging problem to identify exactly where water is coming from because it's characterized by a lot of fracture flow type systems and preferential flow pathways. One thing I will note here is on layer two, you'll see a dark blue colored patch, which is a unique feature in this groundwater system. And it's characterized by lava tubes, and the system is called Pluto's Cave basalt. The way it forms is when was flowing at one point in time, fast moving lava kind of flows through, and it cools down pretty rapidly. And at the surface, as it cools, the underlying flow keeps occurring. And at one point, it leaves back a lot of porous space, and sometimes underneath, things cave in. So it's not a perfect tube, as you would imagine, but it's characterized by a high energy system, which allows a lot of water to flow through it. And that's what we are representing using that dark blue zone. Um, and you will see that a high conductivity is associated with it. It's an important feature because that's one of the features that allows the snow melt and the recharge from up gradient in Mount Shasta and surrounding high elevation areas for water to recharge and transmit through the subsurface and show up at a number of springs in the area. One of the biggest ones being Big Springs, and then there's Little Springs, and there's a whole complex of spring flow that you all know about. So that's what I wanted to point out on this slide. So if we go to the next slide, similar structure in terms of geology and how it changes as you go down in depth. This is showing layer 3 and layer 4 of ModFlow. And as you can see, the footprint of geology shrinks in layer 4 because it's mostly intact bedrock and it's not really participating in the flow process. And that's why you see a sort of curtailed system in layer 4. If we go to the next slide, this is just a lot of detail, but the main point I'd like you to take away is as we were calibrating some of these values as part of calibration, we were making sure that the values associated with aquifer properties for these different groups were reasonable, were plausible. That often in model calibration, if you don't keep an eye on some of these values, some of the errors associated with different aspects of water budget are kind of shoved into these aquifer properties. So this was one of the key things we were trying to do, make sure that these values are plausible, to make sure that the model outcomes are reasonable and reliable. If we go to the next slide. Okay, I'd like you to focus on the left-hand side figure first. It shows the annual average recharge. In the legend, you can see the units are in inches per year. The legend, you can see there's a lot of variation, large range of values. What this is showing is the recharge, okay? The GWI term, the GUI term that John just mentioned, it is a combination of natural recharge and irrigation recharge. And that's what you can notice uh, in on the map. A lot of the agricultural areas is where you will notice high recharge going from land surface into the subsurface. Um, if you turn your attention to the figure on the right, that is what is showing you the proportion of net recharge divided by precipitation. All the numbers greater than 1 mean that the applied water on top of natural precipitation is higher, and that's representing the irrigated water, whether the source of that water is stream diversion or groundwater pumping. The main point is on agricultural fields, you will notice that the numbers are greater than 1, meaning there's a lot more irrigated water applied to these fields than natural precipitation. If we go to the next slide, both these figures are the same, but with different units. On the left-hand side, the units are acre feet per year, and on the right-hand side, just for quick, for for some folks who are familiar with CFS, it's easy to wrap your hands around these numbers. But essentially, both these maps are showing the same information. A few things to note here. What we are showing here is at a ModFlow cell level. So where we have information, we have used that information at a point scale where we know pumping exists. Where we do not know the exact location of the pumping, what we've done is, based on what John mentioned a while ago, we've estimated how much irrigation demand there is. We have information about which fields are served by groundwater pumping. And for those fields where we do not have the exact location of the pumping, we've used the footprint of the served area and distributed that amount of pumping uniformly across that area. So those are some assumptions built in. But the main point is the pumping amount is represented reasonably, and the location is generally reasonably represented with some approximations. The other feature I wanted to point out here is we used the WEL package of ModFlow, and within that, what we've built in is canal leakage. That's an injection from surface water to ground, and we know that we have some estimates on two locations or two streams. One is the Epsom Folk ditch, which is known to leak, and we've estimated some leakage there, where John is pointing to with his cursor. And the other one is potential leakage from Montague Water Canal. And those two areas represent how we represent that in the ModFlow system and how LSPC and ModFlow kind of communicate in representing canal leakages. If we go to the next slide. Okay, so turning our attention from what the inputs to the model are on the outputs now. One of the outputs that we calibrated the model to is looking at groundwater levels. To get things started, ModFlow models or groundwater models need a reasonable initial head distribution. To achieve that, we ran a steady state model. There's some approximations there, but it gets you started. The steady state heads represented in the model represent 1990 conditions, from which point we run a monthly simulation, a transient simulation moving forward. In this map on the right-hand side, we are comparing a 1954 USGS study the head contours are shown in black line, and comparing that against the steady state solution, the green lines. The idea here is not to get the exact match, but because we don't have a lot of information out in the bedrock area, that's where we wanted to see whether the shape of the contours generally conform with an older estimate when there was lesser pumping, just to make sure that we are starting from a reasonable standpoint point. point in time. So that and we were pretty satisfied with this outcome. If we go to the next slide, that's where we are showing a history matching exercise to see whether the simulated groundwater level distribution matches with the observed water level distribution. And this is a scatter plot. This is an easy, quick way to see whether generally the gradients and temporal signature are generally well represented. The x-axis is the observed head data, and y-axis is the simulated head. When I say head, it's the groundwater levels. And in an ideal world, if the model is representing all head values exactly, all the values would fall on the 45-degree black dotted line, but that's not what you would expect from a model. The main outcome here is, are the gradients and the temporal signature generally represented? And looking at the distribution of this on the scatter plot, we can say that the model is doing a pretty good job in representing that. Is it exact at all locations? The answer is no. And for instance, the black circle on the slide is, you will see that the simulated values are more flat than the observed values. When we dig into that, if we click one more time, a hydrograph will pop up. And in that hydrograph, it shows the location of where that example well is. The red line in the time series represents a simulated value. The black dots and lines represent observed values. Okay, and you can see that initially when there's little pumping, the two match quite well. But as time goes on, the black dots, the observed values, show a drawdown every so often, which can be attributed to local pumping in the area. The information is not available to us. And so we are not representing that in the model. And that's where you can see that the model estimated values deviate from the observed values. And that's one of the explanations on some of these deviations. And we've noted this in our report and put out there. And the hope is, as more information become available, and we feed that into the model, we improve the model. If we go to the next slide. Here's one quick snapshot of an average water budget we've estimated for Lake Shastina. These numbers represent average numbers in acre feet per year, average for 1991 through 2023. The main takeaway is these are some of the quantification that we can now put out for peer review and get feedback. Again, as I said, there are a few assumptions built into the model, as with any other model. But quantifying some of these numbers is one of the uses that the model can be utilized. As you can see, the big components in the Lake Shastina budget are the surface water inflow and outflow. And then the next big items are precipitation and then groundwater inflow and evaporation. So it just gives you a quick snapshot on what the big water budget components for that important feature in this system are. With that, I'll hand it back to John.
All right. Thank you, Vivek. Yeah. So as you remember from our quick watershed aerial tour, as we move from the headwaters down to the mouth, the water reduces. And along the way, we have irrigation districts that are pumping and diverting water and irrigating in these respective places. The largest of these districts, the Montague Irrigation District, the Lake Shastina, where Vivek presented the water budget, is a key feature of that system. So what we see in the green is Montague. And I'll highlight this one because it was the most fun from a modeling point of view to simulate. And they had great information in terms of water moving from Parks Creek to the Shasta River, water moving down to Shasta to be stored in the reservoir, water being diverted out of the reservoir. Really, without having that information, there's no way any model can replicate the kind of activity that is associated with that irrigation district. So kudos to them. They have a really great monitoring network and provided us a lot of valuable information that we could use to characterize the movements in the waters in the system. So each of these areas is color coded based on the service areas for each of these districts. In our model, we have to give a diversion point. And so based on, like, for example, here we can see a point where water gets diverted into this service area. And so in our model, all the irrigation demand from the orange footprint, the water is derived from this node in the model. And then Montague, for example, all the irrigation demand in the Montague district, the water is withdrawn from Lake Shastina because that is the source of the water. It has to travel through the canal, but in our model, because we're not explicitly modeling the water movement through the canal, what we can do is a handshake of here's how much water we need, here's where that water is coming from, take that water out of there, apply it over here to close the loop. So that's kind of how it was done. We do have a little bit of overlap, like Vivek described, in the places where we know there's canal leakage. There is excess water withdrawn from Lake Shastina, and the excess that we're estimating is associated with canal leakage. That one is taken out of the surface water model, but it becomes new water at the place where the canal is leaking into the mod flow realm. So that's where it kind of closes the loop on that. So just giving you a little bit, maybe more detail than you care to know, but that's the kind of way that we sort of do the calculations to make sure that we're accounting for the movements throughout the system. Here's a little cartoon that describes the water movements to each of those districts, same color coding that we saw in the aerial map. And I'll just highlight on here the Montague district. So Montague water starts from Parks Creek, the very first slide that we showed in our watershed tour. At Parks Creek, there's a diversion channel where water gets diverted across this little channel into the Shasta River so that it can flow down to the Dwinelle Reservoir. And there is a gauge on that channel, so we were able to have some idea of the water that's moving in that direction. Water that's in Dwinelle Reservoir then gets pumped out into the canal and then irrigated in the air service areas associated with the Montague water conservation district. There are some other details along the way. There are some pumps that are in that system that are used to supplement water. And so we did some analysis, and the report goes into all the detail that you want to know about our assumptions associated with those, like the Pacey well pumps and so on. All of that is documented in the model documentation. But here we have sort of this broad view, high conductivity zone that Vivek described of the snowmelt from Mount Shasta going subsurface, moving down, a lot of that coming up as big springs. Of course, it's not a one-to-one link because the water that you see in Big Springs is a lot older than the water that's going into the ground at Mount Shasta. But there is a volumetric relationship. And there is some evidence that that high conductivity zone is moving water laterally below the ground. On the right, you see a couple different graphs. These are all some of the observed data. And I just wanted to highlight this because in 2014 and 2015, those were two particular drought years. And there wasn't a lot of water movement happening in the watershed because of the drought conditions. The diversions from surface water were curtailed or not happening. And so we see that in the data that we have reported there. Here's that diversion channel. I took a picture from the road that crosses it, but this is the water that is diverted out of Parks Creek. It flows through this channel that you can see here. I was standing right there and took this picture. You can see this channel, and that eventually flows down to the Shasta River and then goes down to Lake Shastina. This is Montague Canal. This is in the sort of like the northeastern portion of the watershed. And I put this figure here because it was really neat to stand and look at one field on the right side of the channel and another field on the left side of the channel. You can see irrigation equipment on the right side, and you can also see that that side is a lot greener than the left side. So there again is just a visual assessment that that there are differences and that the irrigation water movement is happening. I think there might be a question in the chat. I'm not able to see the chat because I only have the one monitor that I'm sharing.
John, I think we can get back to that question after your presentation.
Okay, just wanted to make sure I wasn't
You
moving
can
too
go
fast.
ahead.
Thank
Sure.
you. Okay, awesome. All right. And so here's another sort of evidence from the modeling after the fact. We looked at what ModFlow told us as areas where there's shallow groundwater discharge. So these are areas where water tends to sort of pool on the ground in certain areas, or it could be places where there are some small springs. So ModFlow is sending water back up to the ground, and that water is just sort of lingering on the water surface. And if you walk through the watershed, you do see areas where there is just naturally more water on the surface or close to the surface than other areas. So in a way, it was kind of a neat visual confirmation. And so what we did is this is a map of what the model was predicting. And we took a screen grab from Google Maps and just sort of did an animation. And if you look at this, I'll just go back and forth between the model versus Google Maps. And you can see the places where the model was saying there tends to be water near or close to the surface. Those are the same places where on Google Maps, the satellite imagery shows a lot of green land, and then there's brown around it. So it was kind of a neat sort of a visual validation that the model was doing something realistic in terms of the places where it tended to not, where it tended to return water, aligned with some of these places that were also green on the map. All right, I also called out 2013 through 2015, that drought period. This is another plot, which was one plot that we made almost like the very first time that we set up the model, even before we started linking to ModFlow, before we did anything, we ran the model and we just looked at what the model results compared against the observed data. And I call this out because those two particular years, the model looked pretty close to the observed data without even doing anything else. And those also happen to be the years where there was the least amount of water movement happening. This is a comparison of modeled stream flow versus observed at the Montague USGS gauge. And so, of course, when we link to ModFlow and we move the water, it's able to bring the orange lines back down. But it was just kind of interesting to see that, you know, whenever water is not moved, the model did pretty well at reproducing, you know, the delivery of water to the Montague gauge, at least. All right. We talked about the canal leakage and the water balance implications. Let me just show you some of our final calibrated results. This is modeled versus observed stream flow at the Wairika gauge, so close to the mouth of the watershed. We were pretty thrilled to see that after coupling with ModFlow, the model was able to represent and then also after coupling with ModFlow plus representing all the surface diversions, irrigation activity, all their anthropogenic movements, pretty much all the things that we could get information about to tell the model this is what's happening. After putting all those things in, we saw a pretty strong agreement between modeled versus observed at the mouth of the watershed. Ultimately, that is that's the story that needs to happen. We need to be able to, the model needs to be able to predict the ultimate flow leaving the watershed after all these things have happened. This is the same information, just plotted in a slightly different way. We sort all of the modeled and observed flows from lowest to highest over all time. It's the same time period, 1995, water year 96 through 2012. The same period that was shown here. And this allows us to talk about how the model does for median flows, 5th percentile, 95th percentile, 25th, 75th percentile across the whole hydrologic regime. And what we see is that there is still a little bit of overprediction at some of the lowest flow levels. But again, I want to emphasize that in our approach, we only put in what we have information about. Vivek pointed out the missing information about pumping. That's an example of sort of a data gap that's highlighted as we do the modeling. We realize, hey, if we had that information, that might change the movement of water. And I might submit that that type of regime, when you're pumping out of the low flow periods, those are going to have the most impact on the low flow levels. So if we're talking about 10 to 20 CFS difference, if you're able to capture that kind of pumping and put that in place where and when it's happening, that alone can make up some of that difference that we're seeing here. So it's a great opportunity. It's a great lesson from the model. We want to make sure that we're not over-tuning the model just to make it match the observed data. If we know that there are gaps, we should just be disciplined and wait until we can fill that gap and then let the model tell that story. All right, here's another view. These are some of the calibration statistics. So in addition to the visual comparisons of model versus observed, we also do some calibration using these quantitative and qualitative computational metrics like p-bias, r-squared, NSE, RSR. These are metrics that are used in this field for model comparisons, and there's lots of documentation and guidance that give you some range of, if my p-bias is less than 5% difference between modeled versus observed, that's considered a very good versus good, fair, poor. If we look at the results at Wairika, we were really encouraged to see that almost everything was that dark blue. The places where we had the most deviation was in our dry season, as we saw in the previous one. And those are the places, like I mentioned, where we know that there might be some data gaps, and we want to make sure that we can close the loop on those before forcing the model to match that using parameters. Because that's part of the art and the danger of this type of modeling is you can move the model to match the observed data, but you want to make sure that there's justification behind it when you do that, so that the system is truly representative of what's happening in reality, as close as possible. We know that all the models are wrong, as you've all heard in that George Box phrase. All models are wrong, but some are useful. We want to make sure that we have a model that is useful for purpose at the end of this exercise. All right. So the other dimension of this is unimpaired flows. So what do we mean when we say unimpaired flows? So if we take our calibrated base case model and we turn off all the diversions, we turn off irrigation, we remove Dwinelle Reservoir, which would be quite a dramatic sight to see. We turn off the Pacey pumps in the wells. And then we also have no Parks Creek diversion and no non-irrigation consumptive uses. essentially all the anthropogenic things happening in the watershed, we turn those off and we see what the model does. That's what we call the unimpaired condition. And here is a comparison of baseline versus unimpaired. In this case, the baseline is the blue. It's not observed data anymore. This is the baseline model. And then the orange is the unimpaired. And as you might expect, when you turn off all the water movements and anthropogenic activity, we see a big increase in the stream flow at Wairika. Here's a summary plot that shows 6 different locations in the system. And the top graph shows the average delta in stream flow. And this is average for all years between 1991 through 2023. So the first 3 bars are points along the main stem. Wairika at the most downstream, we're showing about 140 CFS difference if we turn off everything that's happening versus Parks Creek, and then this is the confluence downstream of Parks Creek in the Shasta River, and then the confluence downstream of Dwinelle Reservoir in the Shasta River. That's the 55 that you see. On the right side are some of the tributaries: Big Springs, Parks Creek, and Little Shasta. And this is Little Shasta upstream of all of the irrigation activities. And so the first thing you see is there's not much difference between this one, unimpaired, and baseline, because there's not much happening upstream of that location. So it's kind of a nice sort of point of comparison. The ones where we see the most happening, of course, is Wairika, which is the ultimate mouth of the watershed. And then, interestingly, just downstream of Dwinelle Reservoir, that's another key point where you see a big difference. Dwinelle Reservoir is a key feature within the Montague Water Conservation District's irrigation network. And so by removing the reservoir, there is a 423% increase in the amount of water that reaches that location. So you can see ultimately that essentially trickles down to the difference that we see at Wairika as well. But some of that is sort of balanced out because you have water that would have been moved out of the reservoir and then irrigated and then return flow back to the stream. So some of that would cancel out. That's why you don't see quite as big a difference, as you move towards the Wairika. It's only 89% difference in unimpaired versus baseline. So really neat to just step back and sort of just look at these. It's hypothetical, but it's kind of a neat way to kind of see like, oh, this is kind of makes sense that this might be the projected impact of all of these collective actions happening throughout the watershed. All right. So in summary, I'll just give a couple of key project highlights. Better configuration streamlines the model calibration. We always have this mantra, configuration over calibration. The more time you spend making sure that you have your ducks in line, you have the right information, and then the best information at the right place and time in the model, it takes away a lot of the burden that you'd otherwise have to overcome during model calibration. So that's a key insight. Another thing that I want to highlight is the collaborative effort. This project is probably one of the most complex ones that we've ever had to model. But I want to give a huge thanks to all of the stakeholders and their willingness to share information and to talk about this, especially, given that it's close and near and dear to so many people's hearts. So it was really neat to be able to work in this kind of a collaborative environment. I want to also highlight the Stockholm Environmental Institute. There's an allocation model that we're building together with them where that model can ultimately be used to do some of the downstream analyses of water rights and so on. Another key project highlight is that the coupled model allows us to do a more comprehensive system evaluation. So we can look at the impacts of pumping on recharge back to the stream or seepage back to the stream, for example. Natural influences versus anthropogenic influences. We can kind of tease those apart, as we saw in the unimpaired scenario assessment. Evaporation, evapotranspiration, irrigation demand, diversions, all these pieces, groundwater pumping, diversions, this sort of a comprehensive representation of all the key pieces and actions, these are the building blocks for being able to talk about sustainable environmental flows in a meaningful way. And so I just want to highlight that, and I'll hand it back to Shahab to close us out.
Thank you so much, John and Vivek. So there are a few slides, I mean, just to remind us about some deadlines. Well, the comment period is due by Friday, June 12th. So please submit your comments in a written comment, I mean, via email. Um, so another announcement that we have already made is that we're gonna have a second workshop next week, next Wednesday, on June 3rd. And that would be about the model and running the model and kind of some kind of like technical aspects of the model. To attend that workshop, please contact us beforehand and let us know if you're interested to attend that meeting. We have already received requests, so if you have already done that, your spot is saved in that workshop. If not, please go ahead and let us know by sending an email to this email address. Would you please go to the next slide, John? Well, like always, you can have you can see the latest updates and like regarding the long-term flow efforts for Scott and Shasta in this website. And if you have not already done that, you can, I mean, subscribe at this address and to receive all the notes, notifications, and everything regarding Scott and Shasta. We're gonna share this presentation PDF with you as well as the this recording, so you will have access to these addresses. And next, please. Okay, now it's time to take questions. We have already received some questions via the chat. Well, I answered only responded to only a couple of them, but I believe that we have to review to make sure that we capture all the questions that are in the chat right now. We prefer to have questions, well, verbally. Well, it doesn't matter, but I mean, it's easier to capture all those questions and address them. So if you please go ahead, raise your hand, I will unmute you, and so you can go ahead and ask your question. If you're calling in, please press *9 to raise your hand, and then press *6 to unmute yourself to ask your question if you're calling in. Otherwise, you can just raise your hand and I will make you unmute. Email or your written comments to this address, to this email address. I think we have only one slide left. If you go ahead, John, please. Again, just emphasize that the comment period will due on June 12th. So just to make sure that we have your comments before that time. Before we move on to the questions, I was so excited to start this presentation, so I forgot to introduce myself and the presentation team. So let's do a late introduction. My name is Shahab Araginejad. I'm a senior water resource control engineer with the Eastern Inflow section of Division of Water Rights, the Water Board. Now I ask John and Vivek, please go ahead and introduce yourself. I'm sorry that I missed it at the beginning of the presentation.
Oh, yes, of course. Thank you. Yeah, I'm John Riverson with Alteg, formerly Paradigm Environmental. And we have been supporting State Board on development of the watershed model in conjunction with our colleagues at SSPA.
Hey, my name is Vivek Bidekar. I work with a consulting firm, SS Papadopoulos and Associates. I'm a groundwater modeler, water resource modeler for the past 25 years. And happy to be on this team to contribute to this project. Exciting work.
Thank you, John and Vivek. So thanks everyone for your attention. So we're going to the questions right now. I'll start with the question that Amber put in the chat box. Vivek, would you please go ahead and read the question and answer? And
Sure.
good to have your answer. Thank you.
The question in the chat box is, Amber, the released model simulates several documented spring systems at or near zero discharge. Since these springs are critical sources of cold water, base flow and thermal refugia for salmonids, how will we use this model for regulatory flow setting before those spring systems are independently validated or calibrated? John, since your slide deck is still on, I think that question came around just when you were swapping between the Google image and the spring flow discharge locations. If we go back to that, I want to draw your attention in the Little Springs area. There's a lot of locations, if you see all those blue dots, right, where Little Shasta, not Little Springs, Little Shasta is. That's where conceptually we do represent a lot of the spring flow that occurs in that area, and it's known to occur. We don't exactly match all the locations. First of all, some of these locations are kind of approximate to where we understand those spring flows are. For us, a lot of that came from reports, which we've tried to match up qualitatively. But in terms of quantitative history matching, more information if there's available, specific time series if that's available, and specific locations. If those springs are characterized a bit more in detail on whether it's fractured flow that's connecting some of these springs, or if there's any geologic information to characterize those, that would be super helpful for us to then represent that appropriately in the model and try and history match. As John said, one of our mantras was to try and avoid overfitting and match every observation that we had, unless we had good data to support and justify adding that in the model. So that's my sort of long answer to your question, Amber. Hope that makes sense.
Thank you, Vivek. We have a question from David, both in the chat, and I think I see that Dave's hands is up. So I'm going to unmute you, David, so you can go ahead and ask your question.
Yes, thank you very much. I'm one of the sort of key features of water in the Shasta Valley is that not all water is created equal. Mere volume doesn't serve the need. The real key to the fishery in the Shasta is the nutrient-enriched water as is found in the Big Springs complex. Are you going to be able to use this model to document where water usage for irrigation is impacting the discharge in the Big Springs complex? Not just Big Springs itself, but the complex of springs, some of whom are entering in the bed of the Shasta River and aren't even visible. Since that is one of the key areas where management actions are going to become essential.
Well, I can take a stab at it, and John, fill in if I miss anything. Important question, and that's one of the well, first of all, getting the volumes and flow rates about right is the first step, even if we are talking temperature or nutrients in the future. But getting the flow budgets about right is key. So that's what we've attempted in this round. To answer your question, well, again, if there are data gaps particularly any pumping information, any specific pumping schedules, locations of these pumps. That is key for us to represent that dynamic in the system appropriately. So as this model is out there for peer review, public comment, we are hoping that we'll get some of this information so we can inject that implement that in the model.
Yeah, thank you, Vivek. And I'll add on to that as well. Shahab mentioned the temperature modeling. There was a temperature modeling effort that occurred in the previous, and I mentioned that because the temperature modeling gives us, this effort is focused on hydrology. But David, like your point, great point. Not all water is created equal. The temperature gives us another barometer, if you will, or way to assess what is happening and where and when that water is coming from. And in the temperature modeling, we can see places where water is dominated by spring flow tends to have cooler temperatures, places where there's a lot more return flow from surface water tends to have warmer temperatures. And so that effort is also a valuable piece of the puzzle because it gives us a chance to sort of validate, are we getting, in terms of surface, interflow, groundwater contributions, is that sort of vertical profile of water contribution, how closely is the model representing that system-wide? That the model gives us another great data point to kind of close the loop and assess the performance network wide of that.
I'll just add one more thing. I was just scrolling back in the text in the chat, and David, you have one more question about can you supply a list of data you need that is currently missing? That's one of the things we've added in our report towards the end to identify some of the data gaps. So yeah, we've listed some of these in the report.
David, I see that you have
Yeah,
still your hands.
thank you. I was
Is
wondering
it
if I could then summarize your response to my first question, which would be that you really don't know and can't plot or map the underground flow path that ultimately leads to discharge in this Big Springs complex.
So, David, can I add something? We are very open to receive comments. So we would like to have your comments as a written comment, so we make sure to address that. So if it's not a question or it's a comment, we would like to receive it as a written comment.
I was just hoping for a clarification if I
Thank you. We
understood the
appreciate it.
response.
Sure.
Yeah, so based on the current geology, we have represented and included all the data that we have. If there are any additional well logs that can help us improve that representation, we are happy to do that. But based on the information we had, we have included the characterization the best we could.
Thank you, Vivek. Eli, I see that your hands is up, but let me just go ahead and respond some of the questions that we got earlier in the chat, then I will get back to you. Okay? So, Jennifer, you had a question. I'm not sure if I responded to your question currently. Do you want me to? Well, I'm gonna go ahead and, well, if someone can read Jennifer's question and respond to her, I mean, that would be great. So, her question is on the unimpaired flow and if we can provide monthly basis for various locations.
I think the question is for you, John. The question is, did you look at unimpaired versus baseline by month?
The time series that we presented you can output them at an hourly time step if you really wanted to. So at any location in the system, it is possible to generate time series and roll them up monthly. So yes, it is possible. The model can do that. I'll go back to that. Yeah, these time series, it's summarized on a daily time step in this plot at this location. But every place where there's a subcatchment outlet or connection, um, the model has time series predicted at that location.
Okay, thank you, John. I think that answers the question. Next question is from Ethan. Can you see that question? What was the source of irrigation demand totals to be removed from the unimpaired flow scenario time interval?
I'm missing my second monitor right now since I have this one just now. But based on your rephrasing of the question, the irrigation demand totals that are used were used to calibrate irrigation and return flows for the baseline model. So assuming that that is calibrated and representative of baseline conditions, which based on our comparison of model versus observed at the observed gauges, we feel is pretty representative of baseline conditions. And then based on turning those off and removing them, that gives us what the model would have predicted if those water movements were not in place. So at this point, that's what gives us confidence that we have represented a plausible benefit or impact of, or plausible difference between our base case and unimpaired scenario. But like Shahab mentioned at the beginning, as we receive comments from this and as we close the loop on any of the loose ends that may be out there, those should tighten the modeled estimates of those and give more confidence to be able to run scenarios somewhere between these two bookends of baseline and unimpaired.
Thanks, John. And Crystal is asking, will there be a water temperature component added to this model?
There was a water temperature modeling effort done in conjunction with this for the first version of this model. And I think there is a plan to revisit that. Shahab can speak to that.
That is correct. Yes, that's
to
very true.
revisit this. But there were lots of changes made between the first version and this version of the model. So as you can imagine, those will have to be reconsidered with the temperature modeling as well. But that I'll let Shahab
Yes, Crystal,
talk
we're
more
gonna
to
have
that.
a water temperature tool, which gonna be well, that tool will be using these hydrology model results as a foundation of the hydrology of the system. So the answer to your question is yes, but not specifically as a component to this model, but as a tool that will use the results of this model as an input. So Eli, I'm going to go ahead and unmute you.
Yes. Hello. Hopefully you can hear me.
Yes.
Yeah. Good to see you, John. It's been a while.
Good to see you too. Yes.
Yeah. So I have like a whole slew of questions, but I'll just ask a couple now and then hop back in the queue. The first one is a simple one, and then the second one is more complex. The first one is on the representing snow dynamics. It looks like you have some subwatersheds that are spanning almost all the way from the summit of Mount Shasta, like down to Dwinelle Reservoir. And so is that just using one temperature and precipitation for the whole slice, essentially?
Yeah, some of those subcatchments up there are a little longer. But yes, what the model does, in the case where you have a wide change, a big change in elevation, the model is going to calculate an average elevation for the subcatchment that it'll use to adjust against the temperature associated with that grid point from the observed data. And it'll calculate a lapse rate. And so there is an opportunity to sort of correct for some of that, but your point is really well taken that, if you have smaller subcatchments, then you can have more precision on the estimate of that lapse rate. And some of the other models that we've done using this type of approach, we've started using grids instead of subcatchments for places where you have a rapid change in elevation. And we found that that tends to improve some of that estimate. But at the end of the day, we have observed snowpack at specific points, and we calibrate the model assuming zero elevation difference at those points, and we simulate the snowpack at those points. And then when we apply those parameters back to the watershed, the elevation difference then is used to sort of project that impact on the watershed system. And then ultimately, results are validated based on how much water is predicted in the stream downstream. And so, whereas you might calibrate an exact snowpack location with precision, there might be some error that's introduced when you broadcast those parameters to the watershed level because your elevations aren't precise place by place. But then collectively, as the system kind of rebalances and as you go larger and larger of drainage areas, those errors tend to wash out. But it is a very important consideration. And so part of the rationale for using high spatial variability in our meteorological data is to make sure that every place we can, we're capturing with as much precision what's happening there as possible.
Okay, thanks. Yeah, to me, it seems like it would make sense to cut up some of those where you have really extreme elevation relief to cut those into smaller. The other one was that, so there's definitely a lot of things in the report that are very clearly explained, and I could read them, and I was like, yes, I understand that. One that I did not understand really at all was the agricultural water use. And so I can't understand did it start with the remote sensing analysis from David's Engineering that calculated like a ET time series for every field and across an entire, like monthly time step over the 30-year period. And then you kind of like adjusted model calibration and parameters to try to match that remote sense ET? Or are you kind of assuming that all the crops get as much water as they want, and then the diversions are kind of scaled to keep the crop happy? Or that's just kind of unclear, like some of the links there. And there was other stuff too, like, okay, if a field is flood irrigated, I didn't see anything in the report like, okay, so the irrigation applied is going to be twice that of the ET. So it seemed like there was like some details missing in that section, almost like there should be like a separate little appendix or another few more pages on that.
Sure.
So Eli, I'm sorry, John, just wanted to, Eli, I see it as more like a comment. Would you mind, sending it as a written comment to us? Just to make sure that we can
I'll be submitting a lot of comments. Yeah.
Thank you. Go ahead, John, if it's a quick answer.
Yeah, I just called up these two slides and I kind of went over them pretty quickly in the presentation, but the model gives us the ability to have an ET coefficient that varies by month. And that's for each of the irrigated types of HRUs. We have surface water and groundwater sourced areas. So we can have essentially two different sets of 12 ET coefficients that we tell the model, multiply this against the potential evapotranspiration time series and use that to calculate the irrigation demand. Now, the potential evapotranspiration time series varies from year to year. So the blue bars in here represent that on average over the entire basin. And so our effort was to take what we could with the David's Engineering report and make sure that when we multiply our 12 values times the time series of ET, the long-term irrigation demand over the entire simulation period matches as closely as possible to the David's Engineering. Now, there's going to be some overs and unders from year to year because the reality is irrigation practices are also things that change. The model doesn't have, well, the model, as we've done it, we have 12 values that multiply times the ET time series to get the demand, and that is what is applied over the long term on average to capture the amount of irrigation demand water over time. Year to year, there will be differences. There are more sophisticated ways to capture that by changing land uses. You can turn off irrigation in certain land years and others, but there again comes a thing where like you have to have that information before you go that route with the model. If you don't have it, the best you can really do is to get the most average realistic estimate that you can system wide and then lock that down. And that's the approach that was taken for this effort. It's not perfect, but it is consistent. We're not introducing spatial biases in the system that we can't necessarily defend.
Yeah. So can I ask one clarifying question on that then? So I think you're saying that those the 24 coefficients that you talked about, which I think is like surface water or groundwater for each month, that's applied to those coefficients are applied to every field in the basin. So the model doesn't know the difference between like someone who's got a lousy water right and only has water for half the summer versus someone who has a well that never goes dry that can irrigate as much as they want. Is that right? So it's more intended to optimize across at the basin scale, not the field scale.
That is true, yes. And I want to add one more detail to that. So that is the unit acre of irrigated HRU. The other thing that we have as a variable is in any given subcatchment, we can change the footprint of irrigated HRU. And we did that as closely as possible also to match what spatially was happening in the Davis engineering. So yes, we may not be able to hit that person's field exactly right, but within that subcatchment where that field is located, the total volume of irrigated water is as close as we could match to the Davis engineering, right? Because it's the unit that we can do with the 12 values, but then the footprint is what we use to capture the actual irrigated volume. Because like you said, one person might irrigate more than the other. So that's the way that we're able to represent the volume and the timing.
Okay, thank you. That's it for now.
Well, we have more questions in the chat box. Leah is asking, how do we access the data used to inform the model so we can provide a relevant public comment? Are they presented in the model report?
The modeling report, we tried as best as possible to describe all the information and how we used it. And so, I mean, we'd really be open to your comments on that. If you feel like we did not adequately describe a data set, like Eli's comments right now about this irrigation demand, I'm glad I had this chance to at least give you a big picture view. I think we tried to tell that story that I tried to explain. That is what we attempted to tell in the modeling report. But I can understand also if you are standing in a field and you know that this is how much is getting irrigated in this field, you want to find where that number is represented in the model. That's where I submit to you, like you may not find that. But what we did was at a subcatchment level, the volumes, and then at a unit HRU level, the timing and intensities are as close as we could match to what we had available to us in the data. Yeah.
Angelina is asking, so I think I can respond to Angelina's question. When will the water allocation tool be ready for review? Is that different from the water rights components that the Stockholm Environment Institute is working on? No, that's the same. About the timeline, well, we are focusing on the hydrology model to make sure that we have a very, informative model to feed to be used through the water allocation tool and water temperature tool. I don't have a timeline yet, but a very, approximate or kind of rough. Well, the answer is after wrapping up this hydrology model, then well, we have had a very good progress on the water allocation model so far, but we really need the hydrology results of these model to be used as an input for the other model. So we would like to kind of wrap this model up, then we're going to focus on the water allocation tool. So I don't have a timeline now. David is asking if we're going to have a GUI for the model. So for kind of like modelers be able to use this model. Well, David, we are not planning to have a GUI to this model, but what we are planning to do most likely is to have a visualization tool to kind of show like demonstrate the results of the model for various scenarios and like a post-process tool to the model, like showing the results for various locations and various time intervals. So visualization, we are planning to have a visualization, but not a GUI for the model. We have more questions. So I see a question from David. Vivek, I think that's a question for you. Do you have access to that question?
Yes. The question is, were you able to incorporate areas of impervious hardpan into your infiltration modeling? As I said, we have incorporated all the geologic information that we had, but I'd encourage you to look at the maps that we've provided and provide us feedback if we missed anything.
Okay. And John, I think there is a question for you from Leah. I mean, that's related to her first question, I guess, or is her second question. Do you see that
Oh, I
question?
don't. I will have to stop sharing to see the chat,
No,
I
you
think.
don't need to do that. Let me read that question for you.
Okay, thank you.
One of the first slides showed a demand of 227 CFS for Shasta. Does the report explain how this number was determined?
I'm trying to find that slide so we can talk directly to it. Anybody give me a hand on that? Which slide has
I
that
think it was
number?
one of the early slides. Was it,
Okay.
Leah, was it a table with water demand?
One of the first slides
Oh, I have the slide deck. I
is
can go back and
mentioned,
check which.
and the demand
Okay.
of 227 CFS.
Slide 6. Okay.
Slide 6, maybe.
That's a great question. And we'll have to go and check that. I know this slide that number may not have been updated with the most recent round of results, but thank you. We will check that out. Irrigation demand, I can see if another slide might talk to that because we have yeah, this one is not even quite right because this one is oh, you're not seeing my screen. Sorry.
No, we don't see any
I stopped sharing
slide.
for a second. Okay, here we go. Yeah, I was looking at this one. This one is not quite the same. It's a different units, but yeah, I can't do the conversion to CFS from this right away, but we'll check that out and see. It might be that number in that slide wasn't updated.
So Leah, we will have a follow-up about your question. Does that work, John and Vivek?
Yes.
Okay. So I see a question that was not responded completely from Nick, and I apologize, Nick, that I kind of missed your question. Nick, do you mind if I unmute you so you can go ahead and ask your question? I'm looking for next in my list. Here we go.
I was asking whether the Pacey wells were actually even used currently, or if it was just flying L wells.
So they were rarely used in the time series, but what we did was we looked, and the report has a section that talks about how that was derived. We sort of back calculated periods of time based on what we needed in the model to make up that gap in the water moving past that point in our system. Sort of back calculate the Pacey well volumes and then compare those to what was documented as the frequency and the magnitudes of those. It was really small in terms of the amount of water compared to the other pieces of the water budget, but it was just done just to make sure that it was acknowledged that it does happen.
Thank you. And Eli, I'm going to unmute you.
Yes. I was wondering, is it possible to get digital copies of the data files that were used for the springs flows and the other surface water flows? Not like the USGS data that I can just go download, but in particular, there was some Big Springs Creek data from 2013 to 2018. I was just wondering where you guys got that, because I got some version of the data from Eli Scott at the Water Board that he had just sort of downloaded off the Nature Conservancy system before it was discontinued. And it was my opinion from looking at the data and talking to Ann Willis, who collected it, that data probably shouldn't be used as is, because they weren't like out there. Big Springs is like a crazy place to monitor flows because the macrobites that grow up in the channel and change the stage discharge thing like every month. So I'm thinking that that's what you guys used for that. But anyway, I'd like to get copies of what you have for that. And then also there was like a table that had average flows at some specific springs, but didn't have like the time series of the individual measurements. And I'd like to get that just so I could check that out. And I wondered if that was possible.
May I chime in, John and Vivek?
Please.
So this question of yours, Eli, is very, I mean, I see it very similar to, well, the answer that I had for David. Well, we are planning to have a visualization tool. It's not just a visualization tool. You'll be able to download the results and kind of process even like the input data sets and the results from the model via that visualization tool. So I can refer you to like the visualization tool that we put together for another watershed, Ventura River watershed in South. And it's on our web page. So we are planning to have such a tool. So with that, you'll be able to download the input files used for the model, like from various sources of data, as well as the results of the model for some important, not everywhere, but for some important, locations. But we are planning to do it after this period of comment period, and after responding and addressing all the comments. So that would be the second phase of posting the some files and packages on our web page.
Okay,
And I
great.
can
Thank
follow
you.
up with you. I mean, what kind of data that you are interested in to
Yeah.
make sure that it's included in that visualization.
Yeah. Then another question I had was, are you guys planning to run the model for additional years? Because especially like with flow data, just in the last year and this year, we have flow data. We have really high quality flow data at Big Springs Creek now, which wasn't available before. And so there's some pretty, and there's
Well,
also
Eli, we are not
changes.
planning to extend the simulation
No.
time of the model for now,
Okay.
but well, we'll be focusing on two other tools after wrapping up this model.
Okay. Well, I think that's unfortunate, but that's your decision. Thank you.
We've extended the data through water year 2024, I believe.
Great.
2023.
Yep.
I'm sorry, can you hear me?
Oh,
Now,
I can hear you now.
Okay. Yeah, I was disconnected for a few seconds. So probably I missed the question or something.
no, I
Oh,
just go ahead, John.
we were just commenting that we have extended the model through water year 2023.
I see. Yeah, good point. So I see your hand up. Eli, is that related to another question? Let me unmute you. You can go ahead now.
Thank you. Yeah, different Eli. I just really want to encourage you all to reconsider the decision not to extend the model forward, considering how important the flow of Big Springs Creek is to the entire system, and the fact that we really only have 1 year of accurate flow data from Big Springs Creek, and it is water year 2025. It just seems like without taking that critical piece of information into account when you're thinking about model structure and data gaps that exist, it would be a real lost opportunity from a hydrologic standpoint to not do that. And we do have a plan going forward for the next 3 years to continue rating that gauge and continue collecting data so that we can ensure that we have high quality flow information from that part of the system. That's really, it's the headwaters of the Shasta. So this is really a comment, not a question. Just if you can find the money to somehow include water year 2025, I think it could be very informational when it comes to making sure that this model provides the best results possible for thinking about water use going forward in Shasta. So no need to respond to that. I just want to put it out there. We have really critical data, and it would be it'd be a huge lost opportunity to not include that water year now that we have the data for it.
Thanks for the comment, Eli. Sure. I see another question in the chat. Well, the answer to your second question is yes, David. Uh,
Just for everybody, in case I can't read it, Shahab, did you read that out loud?
oh, no, I sorry. You can go ahead, Dan. Please go ahead.
Yeah, so the question is, you've noted a desire for additional data. Do you have a sense of when you will no longer be able to add to and update the model in the long run? Will Waterboard staff be able to work and update the model on their own?
Well, I don't have an answer to this question. Yeah, the second question will be, well, is since we don't have a plan for that yet, I prefer not to respond to this question yet, but we can look at it as a follow-up question and respond to it later. That's my response. Eli, you are
Yeah.
unmuted now.
Well, if other people don't have questions, I'll keep asking. Um, I, it was interesting because looking through the report, there were some things that like matched better than I thought they would, like the low flows at the mouth of the Shasta. And then there were other things that didn't match as well as I thought they would, namely the storage and Dwinelle reservoir. It looked like, you know, some years it's awesome, and then other years it's like the model is predicting a drought and the reservoir is full. And I just wondered, did you guys sort of drill into some of those years that were kind of misses and try to understand like what happened? Do you think the precipitation data was off, or snowpack dynamics, or was the water management of the reservoir totally different? Like did they, was there some malfunction with the release valve or something, or like any insights there?
Well,
You want me to go ahead?
I can go take first stab at it, and you can fill in, John. It's a highly managed system, and so a lot of activity goes in the Dwinelle Reservoir diversions, and then dam releases and overflow from the weir, and so on. And so when we were able to match some of these quite well, essentially what I'm saying is we attributed the times when we are not able to match to perhaps engineered or managed system where we don't have exact information on diversions, or if there was any shortfall that we are not fully representing, and so on.
Was Montague able to provide you with like a time series of like annual irrigation deliveries?
I guess John can answer that question.
Yeah, we had some. So this graph that I presented, for example, is a summary of some of the time series in the diversion canal. And one thing that you'll see right on here, the blue represents the demand in the model, and the yellow represents the sort of like the actual water that's moved. So you can see there's some timing differences. There's irrigation demand happening in the wintertime, but then the applied water is concentrated between March and October. These are things that we've noted as things that we will revisit. I think a lot of it, some of the imbalances that you see can be resolved by so essentially isolating the water movements to the months where water is being withdrawn instead of relying on demand, if you will, to just come up with that number. So there's some of these refinements that we've already noted, and we've said, oh, once we get a chance at this again, we'll get at it. But then this graph also highlights another point that Vivek was making. If you look at the 2014 and 15, those years, there are no blue bars because there was no water being diverted, right, from during those periods, right? So that's an example of, an operational thing. And as I was describing before, our model, we can get at it in some ways with that, because in our model, we can specify in Dwinelle Reservoir some depth that if the water goes below that depth, no water will be withdrawn. So in a case like this, we can have the model turn off when the water goes below that depth. But it depends on the water going below that depth. And if that water doesn't go because of an imbalance, because of a seasonal difference that happened a month before, you will get a miss. And so it's a very delicate system. But like I mentioned, we have some clues and some things that we are planning to follow up on in terms of some of the timing of these things. Making that blue area fit underneath the yellow area is key to that.
Thanks. Another question I had was, and this is might be a little bit too abstract, but I'll try to give a few specifics, is what kind of things can you change over time in the model? because the like conditions on the ground are changing, right? Canals are being lined, new pumps are being put in, irrigation restrictions are coming into effect and then going away and then coming back. And another thing, I was on the Shasta like groundwater advisory committee meeting call, and some of the local ranchers are saying, "Hey, we had this big fire a few years ago, and we've got way more water coming out of the headwaters of Willow Creek now." So there's I don't think that's like I don't think the fire and land use change is maybe big enough at a whole basin scale that you need to address it yet. But I was just kind of curious, like how difficult of a lift is it to like change the land cover to change like the forest water use, and then the other stuff would be like new wells, canal seepage, that kind of stuff. You give any
It's
comments
really
on that?
interesting that, yeah, absolutely. It's really interesting you bring up that fire example. We have a few basins that we're modeling also for another division of State Board, Big Creek. We have a model of Big Creek and the Big Sur watershed, where more than half of that entire basin was burned over 2016, 2008, 2016, 2021. We had significant fires that changed the landscape. And we're using time variable land use feature in LSPC to capture that. And without doing that, there's no way you can capture the hydrologic changes, because a watershed that was mostly like 60% forest is now like 80% grass shrub because it has burned to that degree. And so we do have the ability to change HRU footprints temporally over time in the model. And I would say when you do that in connection with something like forest fire, where you have, annual footprints of NLCD that you can use as a basis, or some of these temporal satellite images that you can sort of derive that information from, it's great. And you can have information to defensively build that out. But if you don't have information about specific farms and fields and behavior changes and like that kind of high resolution temporal changes, it gets a little harder. That's why we were thankful to have the David's engineering report, because we could make our model fit the central tendency, both spatially and temporally, of that. Because we don't have information about every single field. So that's where it comes in. Now, if that information does become available and we get some more resolution and some more texture, then yes, I think the door can be opened to explicitly represent those temporal changes in the model. But it does require us having the supported information, because if we don't have that, you don't want to tune the model to an outcome based on what you want to see. Has to
Sure.
be
Yeah.
has to be
Yeah.
fit based on what we have
Yeah.
information to defend.
What about the canal lining? Can that be? Is there a system
Yes.
for changing that annually?
I was going to add to that. Yes, canal lining can be changed on a monthly level. So if there is information, but as John said, if you have exact information on when it changed, the reach of streams where the change has occurred, we can incorporate all of that. If you have pumping information, we can incorporate specific pumping information as well.
Great, thanks.
And I would just add that, some of these questions are related a little bit more towards scenarios versus the current unimpaired and impaired scenarios that we have here. So like looking at what would happen if 50% of the canals are lined in these watersheds. Those are things that could be put into a scenario, but we wouldn't be doing that at this phase, because we're just looking at the unimpaired and the impaired scenarios for where we are right now in the model. Because if we don't get these right, then it doesn't matter what scenarios we run. So that's why it's really focused on these two scenarios for this moment.
That was a very good point, Dan. Thank you. And I see a comment from David Webb. David, we need those information. Please go ahead and share it with us. as a comment, you can send it. I mean, those information to us, they are all needed, and we appreciate it. I don't see any other questions, and thank you all for staying overtime. We are after 4 right now. Really appreciate your participation to this meeting. In my notes, I have one question to be followed up with Leah regarding the demand, and one question followed up with David Webb regarding the future of the scenarios, and well, updating the model. Otherwise, we're looking forward to receiving your comments by the deadline, and also seeing some of you next week for the modeling workshop. Again, if you are willing to attend that meeting, please send us your message to include you in that workshop. Again, thank you so much, everyone. Vivek, John, everyone who participated, and I have a very good rest of your day.
Thank you so much.
Thanks for the opportunity to present.
Bye-bye.
Bye, everyone.
Thank you so much, John. That was great.
Thank you.
And Vivek, if you're still on. Okay, I'm gonna stop recording and leaving the meeting. I mean,
Okay.
please see you soon.